In practice, the choice of a particular kernel makes little difference in the estimate. For bandwidth h, define kh of t 1 over h k of t of h, t over h, u over h, you can say. Definition is, what is definition? Kernel density estimator of f of x is f head of x. 1 over n summation I is equal to 1 to 1 kh x minus xi. We can also write this one in this form. 1 over n h summation I is equal to 1 to n k x minus xi over h, where x is a local point. We also call it is local constant. We always estimate the kernel density function at a point and we say that it is x. That check that f head of x is a valid density function, non-negative. So we first check, we integrate this one, f head of x, d of x minus infinite to infinite. Here is minus infinite to infinite. 1 over nh, put the value of f head of x, summation k x minus xi over h. So it will be equal to 1 over nh, summation I is equal to 1 to n, minus infinite to infinite k x minus xi over h. And here we will put x minus xi is equal to u, d of x is equal to du. So it become 1 over nh I is equal to 1 to n minus infinite to infinite h ku du. So here is h cancel, n because of this one cancel. So the remaining one minus infinite to infinite ku du, and it will be equal to and it will be equal to 1, this one. Now we find its mean and variance. Let xi are the fixed and consider a random variable with a density f hat. Then mean, according to the definition, mean is equal to minus infinite to infinite x, expected value of x, f hat of x, d of x. Again we put the value of f hat of x. We have put this value. Again we transform the variables, u is equal to x minus xi. Here we get the d of x, h of du. So this will be equal to, put x uh plus xi 1 over n h summation ku h d of u. So again 1 over n h, that will be the cancel, u this one, d of u. Here is 1 over n summation I is equal to 1 to n minus infinite to infinite xi ku du plus u h ku du. So here is 1 over n xi summation, we have taken common outside. Here is xi this one, minus infinite to infinite ku du plus 1 over n summation h u ku. So this will be equal to 1 over n summation xi into 1 according to the first property of the kernels, and it is according to the second property of the kernel, that will be equal to 0, odd moments equal to 0. So here is 1 over n summation xi. So the mean of random variable with density function is one over n summation xi. So it is very simple, just according to the definition of expected value of x. Here is f hat of x. Just put the value of f hat of x, transform the variables, then split the variable into two parts. Xi is the first part, uh is the second part. Take common xi, then minus infinite to infinite is equal to 1 and it will be equal to 0. So it does not depend on the choice of kernel K and bandwidth H. Very, very important. The mean of the density function f hat of x does not depend on the kernel function and the bandwidth function. Second movement will be helpful in finding the variance of the f hat of x. For the second movement, expected value of x square. Here is same f hat of x. Put the value of f hat of x. Again, transform the variable. Again, and we have this one. Put the value of x and kju h du. Again, solve this one. Solve this one. H square u square kju. So it is the second moment. Here will be the this one. Open the square of this and we get the variance. We get the second moment. Now the variance is very, very important. And according to the formula, it will be equal to the expected value of x square minus expected value of x square. So here will be the minus infinite to infinite x square f hat of x minus infinite to infinite x f hat of x df whole square. By solving this one, we get the variance. Variance of f hat of is therefore the sample variance sigma square x and the sum of the positive linear term sigma square k and h square.